Good morning, students. I've loaded another practice problem to your Canvas account. I would like to work through that problem with you today. It is titled Simple Machines, the Lever. So I'm going to read the problem, and as I read the problem, I'm going to underline important information, and then we're going to draw a picture, and I will complete part A and part B with you. So let's go ahead and get started. A student uses a lever to remove rocks from a garden. She exerts a force of 230 newtons on a lever to raise the rock a distance of 0.16 meters. Okay, so let's go ahead and identify what these values represent. So what I want to do is first, let's go ahead and draw a picture. So let's just say this is our rock, and here we have a student, and she is removing this rock with a lever, okay? And this is my fulcrum here. So she applies a force of 230 newtons. So this is going to be effort force. So let's go ahead and generate a column of knowns and unknowns here. So our force of effort is 230 newtons. And this force is going to be applied in a negative y direction on her end of the lever. So I'm going to use a subscript of E to represent effort. So 230 newtons, okay? And then she raises the rock a distance of 0.16 meters. So right here, this is 0.16 meters, and this is going to be the distance that the resistance moves. So distance of resistance equals 0.16 meters. So on part A, the weight force of the rock is 1,055 newtons. How far does she move her end of the lever if the lever is an ideal machine? So we have our resistance force, which is the weight force of the rock, 1,055 newtons, and it wants to know how far she moves her end of the lever. So this is going to be the effort distance. So I have D to represent distance, and I'm using the subscript of effort. That is our unknown. Now in part A, it tells us that we have an ideal machine here. So that means there's no losses. So there's no inconsistencies in the material of the lever. There's no loss due to friction. It's a perfect machine, okay? So in an ideal machine, we know that the work input is equal to the work output, okay? And work is defined as an applied force through a distance. So our input work is our effort force and our effort distance. So it's the product of effort force and effort distance. And since there are no losses, it's an ideal machine, this is going to equal our output work. Now, our output work is going to be the force of resistance multiplied by the distance that the resistance moves, okay? So we have all of our values except this effort distance. So it's wanting to know how far does this student push down on the lever. So I'm going to isolate this variable on the left-hand side of the equal sign. So I'm going to divide by effort force on both sides of the equal sign. On the left-hand side of the equal sign, that effort force cancels. So we have these three values. Let's go ahead and fill in those values. So in my numerator, my resistance force, remember this is equal to your weight force, so 1,055 newtons. And we're going to move that a distance of 0.16 meters. And we're dividing by the effort force, 230 newtons. Okay? And so what we have here is, let's go ahead and take out our calculator here. So 1,055 times 0.16 divided by 230. This is going to give me 0.734. Now let's take a look at the units. In my numerator, I have newtons times meters, which gives me a Newton meter. And then in my denominator, we have units of newtons. So the newtons will cancel out, leaving us with units of meters. So on part A, I'll just write part A here, our effort distance for the ideal situation is 0.734 meters. Okay? So on part B, it tells us that we no longer have an ideal machine. The efficiency of our simple machine is 84.6%. And the problem asks, how far does the student have to move the lever to lift the rock 0.16 meters with an efficiency of 84.6%? Okay, so what we've got here, let's go ahead and write down our efficiency in a decimal value. So what we're going to do is use the Greek letter eta. Eta represents efficiency. So it is 84.6%. So we're going to convert this from a percent to a decimal value, which is going to give us 0.846. Okay? And so since our input work is only 84.6% efficient, how we're going to set this up is very similar to last time, where for an ideal machine, our input work is equal to our output work. But it's only 84.6% efficient, so we're going to multiply our input work by 0.846. Okay? So I'm going to expand both sides of the equal sign here. 0.846 multiplied by our effort force, 230 newtons, multiplied by our effort distance. Now before we go ahead and plug our values into the calculator, kind of be thinking, since our simple machine is only 84.6% efficient, it's not an ideal machine, will the student have to move her end of the lever a greater distance, an equal distance, or a distance less than what it was for the ideal machine? So let's just think about that. On the right hand side of the equal sign, our work output, this is going to be our resistance force, which is our weight force, which is 1,055 newtons. And then we're going to multiply it by our resistance distance, 0.16 meters. Okay? Now what I want to do is divide both sides of the equal sign by our efficiency in decimal value and our effort force. So 0.846 times 230 newtons. So on the left-hand side of the equal sign, 0.846 and our effort force of 230 newtons, that's going to cancel. Okay, so let's go ahead and take out our calculator. In my numerator, 1,055 times 0.16, this is going to give me 168.8, and we have units of Newton meters, which we know is a joule, but let's leave it in units of Newton meters right now. And in my denominator, 0.846 times 230. This gives me 194.58. And we have units of newtons. So in my numerator, I have units of newtons. In my denominator, I have units of newtons. So that's going to cancel. So 168.8 divided by the 194.58 gives me 0.868 meters. So on part B, how far does the student move the lever? The effort distance. And I'm going to use an additional subscript here to help describe that it is not an ideal machine. It is 84.6% efficient. This is going to equal 0.868 meters. So in situation B, when there are losses in our lever, so the lever is not 100% efficient, she does have to move the lever a greater distance than she did with an ideal machine. So if you have any questions about this problem, please let me know. I hope you have a wonderful day.